Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I hope that all of you are doing very well and having an excellent week so far. And I am excited to discuss with you all on how to use AFT Impulse's new features for AFT Impulse 8. And I'll be covering some of the top new features, and I want to show you where you all can find information about the latest version once it is released. AFT Impulse 8 is just around the corner. It is almost going to be available here very, very soon. We're just putting the very final touches and finishing polishing tests on it and getting it all ready to go. And so it'll be available very, very soon. So how are you able to know when AFT Impulse 8 is released? Well, first of all, if you go to the downloads menu under current versions, followed by AFT Impulse on our website of aft.com, this is where you can always find the latest release of our software. And you'll need to log in order to download software. And so you would click on this login button. And if you don't have login credentials yet, you would just click on register now and you would fill out the form of information. And then once you get your link to activate your registration, you'll then be able to log in with your username and your password. And once you're logged in, it will say hi and then your name, and then you'll be able to go and download the latest version. So one of the things that's really important is to make sure that you are signed up to receive notifications of whenever we put out a new maintenance release or a new version. And so when you sign up for this list, anytime that we publish a new maintenance release or a new version, you'll be emailed to let you know that it's available. And then also that email will give you a direct link to this page where you can then download the current version. So that is one way of being able to be notified of once Impulse version 8 is available. The other way is to sign up for our newsletter. If you're not signed up for our newsletter yet, make sure that you do so. That's where we publish our important information. And so if you go to the support menu on our website and then manage notifications, then you can fill out your box of information, and the AFT newsletter is what you want to sign up for. You can also sign up for the maintenance releases here as well, all in one shot. And that way, you'll be able to hear about the availability of AFT Impulse in those fashions. And once AFT Impulse 8 is available, you will need a new Impulse 8 license number in order to install the latest version, and we'll be giving that to all of the people that have current SUM and the primary SUM contacts. But if you want to get Impulse 8 installed and you're not sure what your Impulse 8 license number is, just call us or email us, and we'll be happy to get it to you. That way you'll be able to download it and install it and get up and running. All right, so let me go ahead and move that aside. And today we're going to talk about the new features of AFT Impulse. And the AFT Impulse screen that I have up right now is the latest version, but it is a beta version, so it is pre-release. So this isn't available yet. So this is what we are currently testing and putting the final finishing touches on. All right. First thing I want to point out, if you weren't aware, AFT Impulse has a couple of add-on modules that can be purchased in addition to AFT Impulse itself to dramatically enhance the capability of the software. And so one of those add-on modules is the Settling Slurry module. It allows you to model solids suspended in a fluid inside a pipe, and You definitely don't want to have water hammer problems in those types of situations to where the pipes can get plugged up and cause the pipes to burst. And so the settling slurry module will calculate what the settling velocities are of the solids suspended in the fluid to help you ensure that your operation is always above that so that you can avoid settling in your piping systems. Also, it will derate your pump performance, and that way when your pump degrades due to pumping slurries, you'll be able to accurately predict what the results are going to be in your system. The second add-on module that's available is the Pulsation Frequency Analysis module. This is really useful for positive displacement pump systems because with that module, it will ring your system with a mathematical hammer in order to determine what the acoustical natural frequencies are of the piping network. And once it determines what those natural frequencies are, it'll then translate those frequencies into operating pump speeds of the positive displacement pump. Those are the pump speeds that you want to avoid operating at. And then it'll go one step further to actually create scenarios for you where it translates that pump speed that you want to avoid into a flow characteristic profile of how the PD pump is going to operate with its pulsation behavior. And you're going to be able to see what the response would be, pressure animations, different things like that. And that way you can see if those pressure pulsations from your PD pumps are going to cause any issues throughout your system. So a really important analysis to do, and both of those are available. And so one of the enhancements that we've made is just making it more obvious on where you can access those modules. So right next to the red status light is the button that says add-on modules. That's where you can access them. And you can read more information on our website about what those modules do. Okay, how else can you find what the new features are for AFT Impulse? Well, if you go back to our website, aft.com, under the products menu, followed by AFT Impulse, you'll be able to go down and see what the features are. And when you go to the page of features, you can then go to the page of new features. And this is a really useful PDF where you can see all the new features that came out with Impulse 6, Impulse 7, and now Impulse 8, all compared with each other. And so if you're behind on SUM and it's been lapsed for a few years, then you'll be able to not only take advantage of the new features in Impulse 8, but also all of the new features that came along with Impulse 6 and 7. And then if you scroll down the second page, this gives you the full list of all the new features in Impulse 8, and I'm going to be covering a few of those today. Once you're in AFT Impulse itself, if you go to the Help menu, there's a lot of information in there. If you need some examples to help you learn how to use the software, under the Help menu, followed by Show Examples, this is where you can pull up the examples help file, which contains many walkthrough tutorial examples that will guide you on how to use the software. And as you can see, there are several examples that will allow you to go through and learn how to use the various features and capabilities of Impulse. So that's where you can find that information. Back to the help menu again, if you open up the main help file, I have to move that over on my other screen here. Once you open up the main help file, on the contents section on the left-hand side, the very first section is called Getting Started with AFT Impulse. If you expand that section, the very first topic that you're going to see is new in version 8, and also version 7 and 6 and so forth. The advantage to looking at what the new features are from the help file is because the PDF here may not do a very good justice because this just has words, but the advantage to using the actual help file itself is when you're reading through this about a new particular feature, you can actually go to that piece of content in the help file to learn more about how to use that particular capability. All right, so let's start things off by showing some of the new features that make the software a lot easier to use in general. One of those is, you know how if you double click on the pipe drawing tool, you can draw as many pipes as you want? Well, this makes drawing pipes and connecting your junctions in your system really easy to do with that flexibility of being able to draw as many pipes as you like. Once you're done drawing as many pipes as you want, you hit the escape button and then you can select things as normal. So that capability has been in there for a long time to be able to double click on the pipe drawing tool and draw as many pipes as you want. So the new thing that we incorporated was if you double click on a junction, you can then draw as many junctions as you like. And so you can, if this is a really large gathering network of some sort, you can draw a whole bunch of wells or reservoirs on your website or on your interface, however you like. And then once you're done, just hit the escape button and that deactivates the double clicked junction drawing mode. And now you have a whole bunch of reservoirs on the workspace. And then you can double click the pipe drawing tool like normal and you can connect them all together however you want. That brings me to my next new feature that I wanted to demonstrate, and that is multi-level undo. That's one of the most critical features that we've all been waiting for a long time, where if you accidentally mess something up or you draw a whole bunch of stuff that you don't want to keep, then the multi-level undo will allow you to reverse those issues. So as you can see, I've drawn a whole bunch of pipes and junctions here, and I might want to undo some of them. So for one, if you go to the help menu and then undo, it's just your standard Control Z. But here's the neat thing about it is when you're undoing operations, you're not limited to just undoing things in the chronological order that you carried it out. You can select any of these. So if I want to delete or if I want to undo adding reservoir junction 17, then it'll undo all of those things up to junction 17. Or I can redo it. And I can keep redoing all of those operations. So on and so forth. And so if I do Control Z, that just continues to undo things one after the other. Now, the important thing that I want to mention here is that the multi-level of undo, it's only for workspace changes only. So if you draw a system and we'll just do something simple here. Any of those things can be undone and redone, which is Control Y. Let's say I want to stretch this out. That can be undone. If I want to select the whole system and move it, that can be undone. If I accidentally break the pipe connections and move the pipe off of the junctions, that can be undone. So it's for workspace changes only. If you actually open up a property window for a pipe or a junction and you specify information and click OK, that's not the type of thing that can be undone. And so if I go back in here after I clicked the undo button, you can see here that it still says 50 for the liquid surface elevation. So keep in mind that the multi-level of undo is for workspace changes only, but that's fine, because that's the majority of things that you might need to undo at some point. All right. So the next thing I want to talk about is our isometric grid, which we have had available for since Impulse 7. So if you go to the Arrange menu and you show grid, you can see the grid to make your models look a lot more cleaned up. And if you go to the pipe drawing mode and change it to isometric, this is where you can work with a isometric grid. Now, one of the things that is painful is a lot of times in the past, if I was doing the two-dimensional grid, let me switch it back. Let's say I have a T and I have my pipes going in this direction. Well, you can take that T and you can use the auto rotate, or you can use the rotation icons on the workspace toolbar to rotate that T so that it points into the pipes. You can rotate this as much as you want. This has no effect or impact on the results at all, but it makes your model look a lot better when the junctions are lined up with the appropriate pipes that they are connected to. So one of the really neat features that we've included with the latest version is the auto rotate feature. So rather than trying to go and click multiple times, if it looks like this, I can select that and go to Arrange, and I can auto rotate the icon. So let's say that I have this system here and I duplicate it, but this time, let's say that this pipe is over here and this pipe is over here, and I want to take both of these T's and point them into the pipes properly. Well, you can select multiple junction icons on the workspace at the same time and go to Arrange and then auto rotate, and it auto rotates both of them for you. That is a really, really nice capability, because with my OCD, I find myself always having to rotate those junction icons to make sure that they're pointing into my pipes, just so that the model looks nicer and more clean. Now, here's something that's a bit more sophisticated, is when you're doing this with the isometric grid, it has a bit more intelligence built in. So I'm going to draw some pipes here. So I'm going to do a piping system that looks like this. I'm going to do one that looks like this. And then I'll have another one that comes down this way. And then we'll do another one that comes down like that. And then we'll do one more. There we go. Okay, so I have well, I guess this is the same as the other one that I just drew, so I don't need that one. All right, so as you can see, there are points here where I would need to place a T-junction in order to connect all of these pipes. Now watch what happens when I place a T on any of those points that have the pipes all together. So if I click and drag the T right on top, look at that. It not only auto rotates it, but it also chooses, if I was to right click on that junction and then say customize icon, it chooses the appropriate orientation for the T of how it should look. And so if I do the rest of these, you can see how it changes them accordingly. Again, it doesn't make any impact on your model results at all, but it makes your model look much better and like you actually have T's connected into the pipes themselves. Speaking of T's, we've also made the property windows easier to work with. So when you open up the T, the default option is to use the simple T loss model. Now, if you remember in previous versions, there's a whole bunch of information here that would need to be specified, which was just really confusing because it wasn't even necessary if you were using a simple T, because there are no pressure losses across a T when you use the simple method. So all of that information does not show up until you click on detailed. So once you click on detailed, now this is where you can pick which type of T that you have. Maybe it's a rounded T, maybe you have an area change or a symmetrical Y. And so each of those options makes it a bit more clear on what type of T that you're working with. Give me 1 second. Excuse me. All right, so that's one option. And then you can also rotate the icon within the property window just like so. And so this just makes it a little bit easier to ensure that you are defining the orientation of the T appropriately. Again, this orientation on the workspace doesn't matter. That makes no difference at all. But if you're going to do a detailed T option, then make sure you get this orientation correct. That way you have correct results and it can help avoid convergence issues, because if you have the orientation wrong, that can lead to potential issues with the solver because it's not calculating the proper K factors. Now, a note on using T's in AFT Impulse. The loss model for the detailed T option is very complicated. It comes from IdleChick, and if you click on the help button, that pulls up our help menu, and you can read about the T and loss model. And this comes from IdleChick, and the equations for the K factors are incredibly complicated. They are highly dependent upon the area ratios around the T as well as the flow ratios around the T. And there's a lot of them. There's a lot of different instances where you might have the flow rate flowing through a T. So you could have combined flow in the straight leg, and then the flow is splitting through the branch. Or you might have flow coming in from the branch and flow from a straight leg, and then they're combining in one of the straight legs itself. The thing is, there's a lot of different combinations that can happen based upon the flow distribution through the T. And that flow distribution is going to lead to different K factors and completely different equations that will be used for calculating the K factors. Hang on 1 second. Apologies, had to rehydrate there. Throat was getting a little bit dry there. Okay, so with these equations being used for steady state situations, that's just fine. It's really not an issue. But here's the trouble that happens in AFT Impulse being a transient simulation. The flow distribution through this T is constantly changing from time step to time step. And so you might have flows reversing through some of the pipes at different times. So the moral of the story is, in a water hammer situation, because that flow distribution changes through the T and it changes very, very, very fast, the correlations that can be used for calculating the K factors on every single time step can be constantly switching. So if you think back to all those different equations that I showed, it might be using one particular equation on one time step and then different equations on different time steps based upon that flow distribution. And so the nature of that can potentially sometimes cause mathematical anomalies, sometimes. And so you want to be aware that that's a possibility. And it may not be appropriate to use the detailed T model in those circumstances because the correlations are changing rapidly. Now, the thing is, the majority of your pressure losses are going to be they're going to be dominated by several other things in your system, such as your long runs of pipe, small diameter pipes, heavy loss pressure or heavy pressure loss components like valves and heat exchangers and filters and things like that. And so your pressure losses through your T's will quite often be negligible in comparison to the overall pressure losses that you'll see in your system. And that's one of the reasons why using simple T's for a water hammer situation is probably just fine. However, if you do still want to account for at least some K factors, here's a couple of different options for you. If you go to the optional tab here, in this area right here called Transient K Factor, the calculated option is the default. That's where it's going to calculate a different K factor for each leg of the T every single time step. Now, if you choose calculated but limited, what you can do is you can specify a maximum K factor. So this is helpful for preventing some of those potential mathematical anomalies. So if your flow distribution is changing very, very fast through that T, that's where you might have some really high K factors, and you might want to limit that to a certain K factor value. That way, it wouldn't create instability issues. Lastly, you can use the option to just simply keep the steady state values. So in this case, it kind of gives you the best of both worlds, where in the steady state simulation, it'll calculate the K factors properly based upon your normal detailed flow operation. However, when you are doing the optional tab of using the keep steady state values, that simply uses a steady state for every time step. So it reduces the complexity, and that tends to work a lot more smoothly with the solver. So just some things to be aware of. All right. So we have covered that. Another tool that is really useful is called the Magnifier Tool, which is this tool right here on the workspace toolbar. So when you click on the arrow drop down for that, you can change the zoom level as well as the magnifier size. I always like to go big or go home. So I'm going to use 200% for the zoom level, and I'm going to use the large magnifier size, and I'm going to turn it on. So here's the magnifier. So watch the mouse on the grid. If I move the mouse on the grid towards a pipe, you can see how the magnifier above is going to zoom in to that part of the model. And so when you have a really large, complicated flow network with hundreds or thousands of pipes and junctions, and things are really close to each other, this makes it really easy to be able to navigate around your model to be able to see what's going on. And so you just move your mouse around. You can still click on things. You can select things. You can change. You can move around your pipes and junctions. You can change connections just like so. And so that's a really useful feature, is the magnifier tool, being able to zoom in to different points of your model. And then to turn it off, you just go back to the workspace toolbar and turn it off. And then you're back to normal. All right. Now we're going to get into some more of the Impulse specific new features that we have. And so for that, I'm actually going to go ahead and open up a pre-built model for you. So give me one moment here. All right. So this is a model that I originally built in Fathom, and then I imported it into Impulse. And so if you don't know how to do that, it's actually really simple. There's nothing to it when you want to import an AFT model across any AFT product. All you do is go to File, Open, and the key thing is when you open up the model files, you have to change the file type right here. And so when you change the file type to Fathom or all, then that's what allows you to open up a Fathom model, and that's what will import it into Impulse. And so I've already done that. So let's say that you want to do some pump transient modeling. This is a system where I'm pumping water up a hill over a elevation change of about 200 feet. And initially the pump is operating at steady state just fine, 500 gallons per minute. Here's what my pump curve looks like. I have a MPSH curve and an efficiency curve. Well, AFT Impulse is all about transients. So if you go to the transient tab, this is where you pick which type of transient you want to work with. So a without inertial model is very simple. So if I was to choose speed versus time, all I would be doing is specifying how the speed of the pump changes over a time profile. It's not accounting for any of the inertial effects on the pump, the fluid, or the motor. And it is important to account for those. So, but the thing is, if you know exactly how fast your pump comes up or down in speed and the profile in which it comes up and down in speed, you could enter that directly and it simplifies the calculations a little bit. However, we have some inertial models which are a bit more accurate because they actually will take into account the total inertia of the fluid, the motor, and the pump impeller. So if you know what the total rotating inertia is, you can specify that directly. But if you don't know what it is, you can click on estimated and it estimates a value for you. Now, how does it do that? Well, if you click on that question mark, it'll give you an explanation of how it's doing it. And then you can click on the help file and read about how the estimations are actually calculated based upon the actual data from your pump curve. So that's one of the new features that we've done is that we've made the estimating operation for the inertia value on your pump a bit more simplified, and we've made it easier to do for you. Now, let's say I'm doing a pump trip transient, and I go back to my pump model. When you're doing a pump trip, the pressure in the line is going to be lost. And when that pressure decreases, you're going to have a tendency for reverse flow in your system. Well, here's the problem. Let's say that for whatever reason you don't have a check valve on the pump. If there's the possibility for reverse flow through the pump, what's the pump head? What should the pump head be in those circumstances? Well, we don't know. This is your pump curve right here. As your flow drops to zero and then it reverses, the pump head that you should use is uncertain. So if you're just using the standard pump curve, which is let me change a different color, which is this option right here. If you're just doing a standard pump curve, what Impulse is going to do is it's going to use the shutoff head for all flow rates that are below 0. So that's just not accurate. So when you have those circumstances where you can have reverse flow through the pump, or if the pump is spinning backwards, if you click on this little animation of a pump, this is normal conditions. So the green is forward flow. So this is normal, and then it changes orange when it starts to reverse flow. So reverse flow is when that flow goes backwards, and it can slow down the impeller. So that's one issue, is reverse flow. We need to be able to predict what's going to happen if we're in a reverse flow situation. And then if our pump can spin backwards, that's a whole other issue as well. So how do we predict what the conditions are going to be? Well, that's what a 4-quadrant curve is for. So a 4-quadrant curve is a bit of a pump curve that is designed to operate in all or it's not designed to operate in all 4 quadrants. It's test data where pumps were intentionally operated in all 4 quadrants. So this is the normal pump curve area that you have, where you have positive flow and positive speed. That's your standard pump curve. So now when I click on this animation again, I might have reverse speed. So that's when the pump spins backwards. So you can see how the orange lines indicate that the pump is not only experiencing reverse flow, but the reverse flow also makes the pump impeller spin backwards. And so that's where you need to have a data set of pump information that can match that. And that's what a 4-quadrant data curve is. And so if you click on automatically selected, this is going to select a curve for you where it tries to match up the best efficiency point of your pump to calculate a specific speed, and it's going to find a 4-quadrant data set that meets your curve. And so the green line with the triangles, that's how your pump is actually going to operate during the transient simulation. So there's a lot of information behind this though. And so make sure that when you're using this option to just automatically select, it will make it easier where it just picks the best data set for you. But being an engineer, you should understand where that comes from. And so if you click on the question mark, it'll give you some more information. And this is where you can read the help file about more details on 4-quadrant curves and how they operate. If you were to choose user specified and then click on specify model, this is how you would do it manually. So if you wanted to specify a 4-quadrant data curve yourself, these are 21 different data sets for 4-quadrant curves that you can choose. And it's based upon the specific speed. So these data sets are from very specific specific speed values, and you want to try and find one that matches the specific speed of your pump. So if I choose this one, which is not even close to the specific speed of my pump, the specific speed of my pump is 1151 GPM units. Where does that information come from? Well, it comes from your flow rate value, your pump head, and your rated speed at the best efficiency point. And so as you can see here, the BEP value, those two curves for the 4-quadrant curve and your standard pump curve, they match pretty well. But here's the issue though, is once your system flow actually starts to get low or higher, this is where the curves deviate from each other. So the more deviation that you have, the less accurate your results are going to be. Now, these are all approximations themselves, though. And so, again, the best way to do it is to just use the one that we've provided for you, and you can see that the curves will match a lot closer. So that's one of the key new features on pumps is we have streamlined the calculation for total rotating inertia to take out your guesswork that you'd have to put in, and we also calculate a 4-quadrant curve for you. But again, those are some very complicated parameters, and it's very important for you to understand where those numbers come from. So be sure to read the documentation on that. All right. So another really powerful feature is the scenario manager. The scenario manager allows you to track a whole number of different operating cases within the same model file. Now, that's not new. The scenario manager has been in our software for a long time, and it's one of the most powerful features, and you definitely want to make sure that you're familiar with how to use it. There's no need to constantly create new models for every time that you want to model a different operating case. Give me 1 second here. Excuse me. All right. So in this particular scenario, what I have done, again, this model comes from Fathom. It was something that I imported into Impulse. So in my steady state simulation, what I did was I started off by sizing my pumps, my pipeline, and my tanks. And so this is how I did that, where I had a certain design flow rate through my pump that I wanted to meet, and I didn't know the pipe size, so I guessed 4-inch, 5-inch, and 6 inches in diameter. And I went through that whole madness to size my pump. Initially, I didn't have a pump curve, so I just did a fixed flow rate value as an assumption. And then once I figured out that the 6-inch diameter piping is what I needed, and I knew what the supply tank height was, my pump, I was able to get a pump curve for. Well, this is operating at 100% speed. Well, obviously, that's not how it's going to operate at all times. There might be situations where I want to operate my pump at different speeds. And so that first family of scenarios right here is where I'm changing the pump speed from 100% down to 85%. So if I was to open up one of those scenarios, let's do the 90% scenario. I open up my pump and I look at that, and so my fixed speed, that's where I set the fixed speed value to 90%. Now, after I created this family of scenarios, what I did was I right-clicked on the VSD scenario itself, and I said, clone with children. When I cloned that entire family, it created this family of scenarios, and then I simply changed the name, low supply, high discharge. So in this particular scenario, instead of my normal operating liquid height of 25 feet, it's only 5 feet. So I only have 5 feet in my liquid, in my supply reservoir. And my discharge reservoir has 215 feet where it's normally 200. And then I wanted to redo the same scenarios where I'm changing the pump speed for each of those cases. So that's where the scenario manager allows you a lot of flexibility. But here's the question is, how do you know if you've specified the input correctly in all of these different scenarios? And how do the changes occur in the different scenarios? that's where we have our new scenario comparison tool. So let's say that I want to compare the input for these scenarios and these scenarios right here. And I want to see what's different in those scenarios for quality checking, troubleshooting, just to make sure I didn't mess anything else up. So what you would do is you can right click on any scenario, and then at the bottom it's scenario comparison tool. So in the scenario comparison tool, your very first step is to choose which scenarios you want to compare with each other. There are some buttons here that make the selection process a little bit easier, but sometimes it's just a bit more simple to go ahead and choose the specific scenarios that you want to compare with each other directly. So I'm going to look at those 8 scenarios, and one of the things I want to do is turn on this option to highlight unique values. That way, if I have a difference in a parameter in any of those scenarios, it's going to highlight it for me. That way I can quickly and easily see what has changed. Now, we have 3 sections right here, and all of them are collapsed. So let's look at each of these individually. The first one is select pipe and junction properties. So this is where you have a whole list of input properties for your pipes and your junctions. So these are general component parameters, pump parameters, reservoir parameters, valve, etc. So there's a lot of parameters that you can compare across different scenarios, and this is where you would choose which ones that you want to compare. If you're only interested in something specific like hydraulic diameter, just check the box for one of them and it'll make it a little bit easier when you compare them. But let's go ahead and do all of them. So we're going to compare all of the input parameters for everything. Next, let's look at select general properties. So the general properties, such as your solution control, your fluid property information, your sectioning, your transient control, all of those are things that could possibly be different in each of these different scenarios. And when you check those boxes, it would allow you to compare those potential differences for those general pieces of information across different scenarios as well. Lastly, you would have to select specific pipes and junctions that you want to compare. Well, if you're only interested in a couple pipes and junctions, you can just select those manually. But here, we want to do a full spot check. I want to see anything that is potentially different in any of those scenarios at all. So now, once I've gone through and set all that up, I would click on Show Comparison, and I'm going to maximize this, and there's a lot going on. So let's break it down. First, let's take a look at what the items are. So right now, this is set to compare all of the items. Well, the items include all of the pipes, each of the junctions, and all of the general pieces of information as well, like solution control, system properties, etc. So those are what the items are. And as you can see, it's set to look at everything. Now, right now, here is where it's set to show parameter differences only. So as you can see, it's only showing a few parameters. Let's see what this looks like if we set it to all parameters. When you set it to all parameters, this shows every single input parameter for each pipe and junction. So these have all of the parameters here for pipe 201. And there's a lot of scrolling that you're going to have to do. So if you just keep scrolling and scrolling and scrolling, here's pipe 202, pipe 203, 204, 205, etc. Now, there's a lot of colors that goes along with this, and the colors mean something. So down below in the bottom left-hand corner, there are color codes for the item column and color codes for the parameter column. So if you look down at this, it tells you exactly what they are. So the item right here, if you see a item in green, like pipe 202 or pipe 201, that means that all parameters for that pipe are the same. So if it's green, that means that you have no differences for any parameter in that particular pipe. Now, in the parameter section, if it's green, that means that the parameter is the same in all of my different scenarios. If you have a parameter that is not the same in every single scenario that you're comparing, then you'll see that it's highlighted in yellow. So this is where using the filter is really helpful for showing simply your differences. So right now, I don't necessarily care about seeing all of the parameters for all of my pipes and junctions. You can copy all that information and put it into a spreadsheet, or you can print it out if you want. But I want to see what's different. That's the important thing to focus on. So for that, I'm going to choose differences. And so now, as you can see what this did for all of my pipes, it collapsed all of them. So because all of my pipes are exactly the same in all my scenarios, I don't have to scroll through and look at any of the pipes. I can come straight down and I can look at junctions that are different. Now, as you can see here, junction 201 is yellow. That means at least one parameter is different. Well, what's the parameter that's different for the reservoir? Liquid surface elevation. So again, the filtering just helps you narrow down the actual differences. So I'm going to filter the differences on the parameters as well. So everything is filtered to the maximum level. So the only thing that I have differences for are these three junctions: my supply and discharge reservoir and my pump. And what parameters are different? It's simply the liquid elevation, the speed, and the liquid surface elevation for the other reservoir. Now that I have everything filtered, I can focus on what the values are in different scenarios. So as I go along here, I can see that in my 100% speed scenario, here's my regular liquid surface elevation, and then my pump is at 100% speed. So all of these are the same liquid elevation for my supply and discharge, but you can see by the different colors that it's the pump speed that has changed. And because the liquid elevation is the same for these reservoirs, you can see how the colors there are the same. However, when I scroll over to the right, you can see that in the whole other set of scenarios, I have a different liquid surface elevation for supply and discharge, 5 feet and 200 feet, or 215 feet, but you can see where the pump speeds are different. So that is the scenario comparison tool, which makes it really a lot more friendly to be able to see which parameters have actually changed in the various scenarios. If you need to go back and throw in some other scenarios, just click on Modify Comparison, and that'll take you back to this window where maybe you want to look at an exhaustive comparison for every single scenario in the model. So that's one of the new tools that we're really excited about with the new version here. All right, last two features that I want to demonstrate today. And I'm able to actually show them together, and it's really powerful. So let me close this down, and I'm going to open up a new instance of Impulse. So there's two features that I'm going to demonstrate here. One of them is multi-scenario graphing, and the other is time-varying friction. So both of those words may be kind of foreign, but you're going to see exactly what I mean. Okay. All right, so here's what I have. In this particular model here of my piping system, I have a flow path where I have a pump, and then the flow continues down the line. I've got a flow control valve that regulates the flow. I have another incoming flow from this point, and then I have a booster pump later down the line, followed by a second flow control valve. And then finally, I have a valve near the end of the line, and the transient in my system that is causing things to change is a valve closure scenario. So this valve is set to close within 40 seconds. And as you can see, the very last part of the closure happens at the very end. So 40 seconds is how long it takes our valve to close. So what I did was I created 3 scenarios. So I want to take a quick sidestep back to our website really quick and show you our blog page. If you go to aft.com, we have tons of tips and tricks articles which are really helpful for helping you learn the software more effectively. So under Learning Center, go to Tips and Tricks, and you can see lots of outstanding blog articles that will give you more insight on how to use the software in different ways. There's a blog article that I wrote a while back called Variable Resistance. So make sure that you remember that article, Variable Resistance. When should you use variable resistance? Well, if I open up that article, I'm sure that if you're an Impulse user, you've probably seen messages that look like this, where it tells you that you have constant friction factors being used, where in reality your friction factor changes, which is obvious. If you're doing a transient simulation and your flow rate is changing, your Reynolds numbers are changing, your friction factors are going to change. Typically, they're not going to change very much. And so what this is telling you is the initial friction factor in steady state flow, and then what the friction factor could be at maximum flow. And so as your flow rate gets higher, your friction factor would potentially decrease. And so the issue is, if your friction factor changes a lot, would you want to continue using the steady state friction factor value for every time step in the simulation? And you may want to allow that friction value to be able to change. Well, this article walks you through what those warning messages mean. And in previous versions of Impulse, it looked like this. In the transient control window, if you wanted to allow the friction factor to change on every single time step, this is where you would turn on variable resistance. The variable resistance would allow your friction factor to change on every single time step instead of only using the steady state values. The question is, does that really even help? Because it does allow, or it does cause your runtime to be a little bit longer. In the past, it's been, on a factor of 3. Well, in the latest version, AFT Impulse 8, we've been able to reduce that dramatically. So now it may not be such a sacrifice in runtime to be able to get a little bit more accuracy by allowing your friction factors to change. But the moral of the story is, in previous versions of the software, the results hardly changed at all. So here's one example with the pump speed trip that I'm doing, where it compares variable resistance without using variable resistance. There's no differences there. Here's the maximum minimum pressure profile. Same thing, no differences. Situations where you might want to use variable resistance would typically be when you're doing a pump startup scenario. So if you're doing a pump startup scenario where you initially have no flow, your friction factors could potentially be a lot higher before the transient simulation starts. So that's a situation where you wouldn't want to be stuck with those larger friction factors once your pumps come up to speed, and you'd want a model to reflect that. However, when you look at the analysis that I did, you can see that the results are virtually identical with each other. There's really hardly any differences in results that you would see by allowing those frictional values to change. And so in a lot of cases, it just may not be needed to have those friction values changed. But now we have some more accuracy. We've been able to increase the runtime and the speed of that. So that's where I compared these three options for this system. So in my first scenario, if I load the constant friction, this is like the same thing it was before, where I'm using my constant friction factors every time step during the simulation. So now pipe friction during simulation, it's up here. So I'm doing constant. And then the second scenario is time varying. And so if I go to transient control, this is where I chose time varying, and there's two options. There's simple, and then there's advanced. So time varying simple, this is the same thing as simply turning on variable resistance in previous versions of Impulse. So that's the same thing that we saw in that blog article that you would see there. Here's the new one though, time varying Bernown. So this is where we have a different mathematical model that's more advanced, which uses a model to allow the friction factor to change more accurately during a transient simulation. And our help file documents that. I'm not sure where it is. Let's try keyword search. So the Bernown model comes from this resource here, Adamkowski and Lewandowski. So that'll give you more information about this more advanced simulation option. Now, again, for the majority of models, this is not going to cause a difference. But in this particular model, you actually see a difference. Now, first, let's take a look at the constant friction scenario. I've already ran the model to get results just for the sake of time. So let's take a look at this flow path here. If I select the flow path on the workspace first, and then I go to the graph results window, I can click on profile, and I'm going to do an animation. So this stuff isn't anything new. So here's my profile, and when I click on the play button to animate things, you can see how the time changes in the bottom right hand corner, and it's changing very, very slowly. It's not even up to 1 second yet. And keep in mind, this valve in this model is closing in 40 seconds. So I'm going to fast forward a little bit. So now you can see that things are starting to change. And so we'll play this. And so the valve is starting to close almost all the way. And then once that valve is fully closed, then you're going to see how the pressure oscillates through the flow path of those different systems. I apologize if there's a little bit of a lag. It looks like there might be a little bit of a lag just because of the webinar. But what you would see here is the pressure wave that's bouncing back and forth, and it's not very severe. It's not really causing, extremely large differences. If I speed up the animation, uh, you can see how this is appearing to change a little bit more violently. But again, this, is it something to be concerned about? Maybe, maybe it's not. I mean, you'd have to do the analysis. But here's the thing I want you to pay attention to is the time. It's almost a minute, and you can see how these pressure waves are oscillating significantly. Well, how does that animation change with the other scenarios? If I want to be able to look at this exact same plot for the other scenarios, wouldn't it be nice if you could plot all of those three scenarios together for the same flow path? Well, the answer is now you can. Here's how you do that. I simply go back to the graph control tab. Here's where you see multi-scenario. By default, it's doing just the current scenario. So what I'm going to do is I'm going to click on this drop-down menu, and I'm going to turn on the other two scenarios. So you click on Select Scenarios, and I'm going to add these two other scenarios to it, and then regenerate the graph. So now you can see that initially all of the results are exactly the same for steady state. I'm going to fast forward again. And so we're at about 43 seconds. So we'll play this. So the valve is fully closed. Now I want you to focus on the differences. Follow the yellow line. The yellow line is the one that is using the most advanced method for allowing the friction factor to change time step to time step. I'll click on the default speed. So as you can see, there's not many differences yet, but the blue and the red lines are sort of going a little bit higher than the yellow lines over here. And now you can see there's a little bit more deviation in that part of the system. It doesn't look too severe, but keep in mind that these are pressures in bar gauge. So this is about 30 atmospheres right here. So it's pretty high pressure. Now, the thing to notice here, especially if I was to speed up a little bit more in time, now we're at 62 seconds. See how the yellow line is hardly changing? What this means is that the yellow line is pretty much dampened out. So when you see that the blue and red lines are still changing significantly with those other friction models, constant and time varying, if I was to uncheck those and just play the yellow one, as you can see here, the time is changing, but the values are not. So you can see that with using the time varying Bernown equation for friction that's allowed to change, then that allows your system to dampen out much faster than it would appear with using constant or time varying friction, which would be constant or the original variable resistance. Now, this becomes a little bit easier to see if you were to focus on different parts of the system. So I've already created some graphs that does that. So you might want to take a look at what's happening at control valve J7. Well, let's look at the inlet and the outlet of that flow control valve. I've already done that. So when I go back to my graph results, that is J7 control valve inlet and outlet pressure. So when I regenerate this graph here, just got to give it a minute. Hopefully it doesn't crash on me. My computer seems to be cranking pretty hard. There we go. So as you can see, I'm using the option to look at the 3 scenarios again. I clicked on that and I said select scenarios, and I'm looking at all 3 scenarios and it's plotting them all together. So that's a really powerful feature. And as you can see, it's plotting everything, which might be a little bit much to look at. So let's break it down with the checkboxes. Let's just look at the inlet of the control valve. So here's constant friction. This is using the same friction factor for every time step. As you can see, there is a significant amount of noise in there. Now, let's turn on the variable resistance, which is what we call now time varying simple. As you can see here, when I turn this on and off, you can see that the two graphs compare fairly closely with each other. But the time varying simple does smooth things out a little bit more. But what about the time varying Bernown? Let's look at that one. It doesn't help that they're very close in color. So here's the time varying Bernown by itself. As you can see, it's got a bit of noise up front, but look how fast that dampens out. And so if I turn on the previous variable resistance, you can see that that's a significant change. So you have a lot of water hammer, but that dampens out really, really fast. And this is the same idea for the outlet of that control valve. Here's the variable resistance, which is the green. When I turn that off, you can see how it dampens out much faster with the Bernown, which is allowing the friction factor to change with the advanced method. Let's take a look at one other area. Let's look at the pump. So this is the second pump in the flow path, and you see something very, very similar here. When we take a look at the top one, so this is the pump discharge J9 right here. So this is the constant friction, and I'll turn on the variable resistance. I'm going to turn on my rangefinder. I'm going to zoom in to between 40 and 80 seconds. So as you can see, these are very similar. So this is regular steady state friction values at every time step. This is turning on the what was previously known as just including variable resistance. Not much change. However, when I turn on the time varying with the Bernoulli equation, look at that. If I turn these off, you can see that it dampens out so quickly and there's no noise of those oscillations. So those are, mathematical artifacts. And so this is something that's a really powerful new feature of Impulse is, there's a lot of times where we've gotten tech support tickets from people asking, shouldn't the water hammer waves be dampening out faster than they are? Before, with the constant and variable resistance options, it would look like it would take a long time for those water hammer waves to dampen out. But now that may not be the case because we have this advanced method of being able to calculate how the friction factor changes all throughout the system for every pipe. And you can see it makes a massive difference where it dampens out within 20 or within about 10 seconds, and then it flatlines. So that's more accuracy, and the runtime is not as extremely long as it used to be because we've been able to add methods and performance enhances that make that run faster as well. Okay, well, that concludes the webinar for today. And I want to thank you all very much for joining me to learn more about the new features that are coming very soon with AFT Impulse version 8. Stay tuned. It should be released here any day. So keep an eye on our newsletter and our maintenance releases and our website, and we'll be alerting you soon once it's available. Thank you again, everyone. Take care and have a wonderful rest of your week.